presentation on some of the challenges that come with using lithography-based ceramic manufacturing to make stepped impedance type filters. The outline for my presentation, I'll provide a short motivation and background, then an overview of normal ceramic manufacturing process and the additive manufacturing version thereof. Then the lithography-based ceramic manufacturing process, I'll provide some details. Then investigated some dielectric variability using this additive manufacturing. Define a filter prototype that we used as a demonstrator, then some pinhole optimizations issues that we encountered, and then provide some conclusions. So the motivation for this, why we use additive manufacturing, it's becoming a more key or disruptive technology in the microwave industry. You can greatly reduce complexity costs associated with manufacturing. You can sometimes enable rapid prototyping depending on the application, and you can manufacture geometries that are simply not possible with conventional subtractive manufacturing technologies. And then why use ceramics? Well, compared to plastics or other conventional substrates, ceramics can have very high dielectric constants while maintaining low losses. The dielectric constants also, high dielectric constants enable a great degree of miniaturization of the EM fields due to concentration of the EM fields. And then due to high center temperatures involved in the manufacturing process, you can have very temperature stable components depending on how they are put together. At the bottom, there are some machine specifications and material specifications. The company that I worked with on this project is Litos. They are based in Vienna in Austria. And the material that was used is alumina with a dielectric constant of around 9.5, and it's very low loss. A more conventional ceramic manufacturing process is you have some sort of powder preparation, whether that's ball milling or grinding of the material. Then you need to shape the powder, so molding or casting it. Then the shaped powder goes through a drying or debinding phase, and then it's fired and sintered to produce a final part. And for the additive manufacturing approach, in this case, you replace the powder shaping portion with an additive manufacturing step. This includes a CAD model design. You convert this CAD model to a printable file format. You slice this model into the printed slices. Then you print the object, and in this case, you require some post-processing in the form of cleaning. The lithography-based ceramic manufacturing process uses an optical projection system that projects each layer through a slurry onto a build platform that hardens it out. So some of the steps that are involved in this printing process, you need to prepare a build platform, and you can see roughly the size of a typical build platform that was used. Then you have a pre-dosed vat that you use to start the print process, where you need to set a reference level for contacting. Then you can load your print job and begin the printing, and the parts are printed hanging from the build platform. And the projection is done through this photosensitive slurry onto the build platform for each layer. Then in step 6, you can see that the parts come out covered in uncured slurry, and this uncured slurry needs to be removed before you continue with the process. Otherwise, you will have undesirable parts, or you will have increased infills that you didn't design for. So this needs to be removed. And this is done using a solvent and airbrush normally. And you also need to remove this from the build platform. Once this is done, you send it for debinding and sintering steps. And this process comes with some design rules that you need to follow depending on the material and the print. So you have minimum and maximum wall thicknesses that you can achieve. You can have maximum overhangs that you can print without supporting structures. The orientation of the print will greatly influence your surface quality and your print resolution. The support structures will be required depending on some orientations. You will need to provide access for cleaning of any hollowed areas. You need to compensate for shrinkage during the sintering process, as the parts can shrink, for example, in alumina up to 25%. And then you should chamfer sharp edges around them to avoid stresses during the sintering phase. So the first part of this project was to investigate how easily you could influence the dielectric constant using these printed ceramics. And so some alumina wedges were printed where the lattice was kept consistent, but the infill percentage was varied. And this was varied from 80 to 30%. However, the 30% was not stable enough to survive printing, so we only measured 80 to 40%. And these did not perform particularly well. They were quite difficult to clean as the narrow channels become almost impossible to remove all the slurry, as you can see on the right-hand side. And these achieved dielectric constants of around 8.7 to 5.9 from a reference of 9.5. And then the next step was to try some fixed infill percentage lattices and then changing the lattices. Because in theory, if you have a lattice structure that's small enough compared to your wavelength, the lattice type is somewhat arbitrary. And so various of these wedges were printed and dielectric constants of around 3.8 were consistently achieved. So this was much more suitable lattice types than the previous tested ones. Then using these lattice type structures and solid alumina sections, you can implement a stepped impedance type filter with evanescent waveguide sections that act as impedance inverters, and you sandwich a high impedance section between two low impedance sections. And using this, we made a fourth order filter centered around 8.8 gigahertz as a prototype test. This filter, due to the measurements where we showed that the lattice type is somewhat arbitrary, you can first use in your optimization somewhat homogeneous dielectric substitute blocks for initial optimization. This greatly speeds it up. And then when you have your final dimensions for your filter, you can replace these homogeneous sections with your actual lattices to compensate for any deviations. This filter was then designed to include SMA pin feeding, so there's a waveguide to SMA section included on each side. And the intention is to eventually metallize this filter. However, to simplify the process in the beginning, it was decided to mill a cavity for this filter, which provided its own challenges. As you can see in the photos, this filter was slightly smaller than the cavity, and there was some warpage in the print. And this was investigated further compared to the reference design. And it was found that the primary discrepancies in the expected shrinkage to the actual design came inside the lattices. And when these lattices were investigated further, you could actually see that the hollow sections are smaller than they should be, and the interior solid sections are actually being pulled apart. And this is an unexpected behavior. So to try and address this issue, the first assumption was that the shrinkage deviations were to do with the sinter process, where the uneven heat distribution causes the object to sinter in different ways. So the solid alumina sections will sinter slower than the less fill alumina sections. And to try and see if we could compensate for this, we introduced different lattice patterns where the supporting elements were at 45-degree angles to the direction of shrink, and also to try and different sizes of the lattice elements to have thicker elements to see if this helped to compensate this. And this had very little effect on the actual final outcome, so this is not the actual contribution factor. After discussions with the experts at LITOS, it was suggested that it could be due to the friction of the printed part on the inside the oven, on the floor of the oven. So the solid alumina sections have a much higher friction coefficient than the open lattice sections, and this causes the solid sections to be stretched while the lattice sections get shrunk. So one way to try and address this is to print sinter guides, and these are printed in the same print run as the filter prototype. And then you can stack the filter prototype on these sinter guides, and these guides help to pull the filter into actual the desired shrinkage range. And then also, as you can see on the right-hand side, some of the prints, if you're printing very fine lattices, it's very easy to damage these during cleaning as you're using air pressure, and these lattice structures that I printed were very, very fine to try and see if a finer lattice structure could assist with the shrinkage. So these still need to be optimized further to see if we can resolve all the issues with them. Another problem that came with the initial prototypes is that the SMA pinholes, it's difficult to get consistent sizing to fit the SMA pins. And because of you're going from a high dielectric constant, if you have an air gap, you'll have a high impedance between the pin and the dielectric. So you need to have quite a good seal in between the two. So you want the hole to be as accurate as possible. So to do this, various samples were printed with differing pixel a few pixels added and subtracted onto each to see what is the optimal sizing for this. And then based on that, after sintering, you could determine and measure which one was the perfect fit for the SMA. And that was implemented into the filter. However, it was not taken into account that the filter section is much wider than the test wedges. And these test wedges undergo less overpolymerization, and due to this, the holes shrink even further on the filter. So it's important to take into account the final width of the part that you're trying to print, otherwise you end up with inaccurate results. So some conclusions, printing lattice structures, you need to base it on strength, cleanability, and the desired infill. It needs to be a balance of these, and these will need to be chosen and optimized based on the requirements in your design and the orientation that you need. Then the cleaning and sintering steps are very critical to the successful component. The printing portion is relatively accurate. It's the sintering and cleaning that introduce more variables into the final design. Then your initial designs can be simplified using equivalent dielectric blocks, and then optimized, compensated for later. And the entire process flow is very important with this additive manufacturing approach. And the design needs to be adapted at each stage iteratively to match this process. And for microwave applications, the tolerances are still quite difficult to achieve for optimal components. Thank you very much.
Okay, thank you, Luca. Does anyone have any question for Luca? Okay, Jason.
Okay, yeah, and Luca, thank you very much for this interesting talk.